Assalamu alaikum, dear student. Today is the third lecture of week number 2 and we are studying the pressure and fluid static, which is chapter number 2. In today's lecture, the topic we are going to cover are pressure at a point, basic equation of pressure field, and different cases under this heading. The case number 1, the pressure in a stationary fluid under the action of gravity, the pressure in a stationary homogeneous incompressible fluid. Case number 3, several fluids of a different specific weights. Case number 4, interconnected vessel. If the time allowed, we will discuss these topics. Otherwise, the remaining topics will be covered in the followed lecture. So, the first topic we are going to cover is pressure at a field, pressure at a point. So according to the Pascal law, what is pressure at a point? The pressure at a point in a fluid at rest or in motion is independent of direction as long as there are no shearing stress present. We extend this statement and we say that we are going to prove that the fluid pressure is transmitted equally in all directions throughout the fluid field. Or we can say that prove that how the pressure at a point varies with the orientation of the plane passing through the point. It means that throughout the plane, whatever is the orientation it is, the pressure remains same at a point. So this we have to prove that. So to prove that, consider the free body diagram within a fluid mass. So this is the fluid field and here we are considering a small wedge-shaped fluid element which is almost considered as a point. Since the fluid is at rest, there will be no shearing force on the face of the element and the element will not be accelerating. That means there is no solid body or there is no rigid body motion. The only external forces acting on the wedge are due to the pressure and the weight. The pressure, that is atmospheric, as well as the pressure due to fluid itself. So consider the small wedge portion of a stationary fluid having dimensions dx, dy and dz along x, y and z axis respectively, as it is mentioned here in the free body diagram or in the sketch. This is our x-axis, this is y and this is z-axis. So the dimension of the fluid element in the x direction is del x and the dimension in the y direction is del y and the dimension in the z direction is del z. Since the fluid element is almost approaching to 0, so these dimensions are very small. We are not considering only the standard reference axis. We are not considering only the pressure acting along the standard reference axis, but also we are considering some irregular reference direction, that is PS, and it is acting with the angle as, just to prove that the pressure acting at a point is not same only in the standard frame of reference but also in the all frame of reference or in the all directions. So that's why we all know the pressure always acting perpendicular to the surface. Okay, so here this pressure is acting perpendicular to this surface. This pressure in the z direction acting perpendicular to this surface. This is the surface, and here the pressure acting perpendicular to this surface, and the dimension of this surface is del S by del X. Let's move on. The pressure acting on each standard dimension is Px, Py and Pz along the x, y and z direction. Now we are going to see what are the forces acting along these directions. So consider a pressure P acting on the inclined plane. So this is the pressure P acting on the inclined plane, which is the center of the fluid element. Okay. So now we are going to observe forces due to the pressure acting on each surface. The force acting in y direction due to pressure Py, which is equal to, we know that the pressure is force per unit area. So the pressure in y direction, the pressure in y direction is the pressure force in y direction is Py dx over dz. So this is the pressure in the y direction. This is the y direction. The pressure multiplied by the area. What is the area? This is the surface area, del z into del x. Now the force acting in z direction, that is the pressure acting in z direction, is Pz, and the area at which this pressure is acting, so this is del x and this is del y. So Pz is equal into dx dy. For simplicity, the forces in the x direction is not considered. So weight of the fluid element, we know that, which is acting downward. So what is the weight of the fluid element? Is the weight density multiplied by the volume of the fluid element. So weight density is equal to gamma, which is equals to mg, which is equal to rho g, and the volume of the fluid element, we can calculate the volume of the fluid element half base into altitude. Okay. So what is the base? Base is half del y into del x into altitude, that is dx dy dz. So since the fluid is stationary, so no shear stress is acting on it, we can apply equilibrium condition as sigma Fy is equals to 0. Now we are going to apply the Newton's second law. Since the fluid is not moving stationary, so Fy is equals to 0. So all the forces acting in y direction we are going to consider. So the forces in y direction, this is Py del x del z. So and the component which is balance this force in this y direction is the Ps component, which is equal to Ps del x del s sine theta. Okay. So the component of this force which is acting on this surface, okay, which is equal to, this is del x, this is del s, and this is the component, this is the component which is balancing this y direction, which is del x del y sine theta. In the same way, the forces acting in z direction, which is equal to Pz del x del y, this is the force, and there is another component of this surface force which is balancing this force, that is Ps del x del s cos theta, and also the weight which is acting downward, so that is weight of the fluid element, W is equals to 0. So the upward direction we are considering is positive, and the downward direction we are considering negative. So here we are going to see the forces acting along the y-axis are equal to this, and we can say that from the figure sine theta is equals to del z by del s. How it is? So this is our theta, and this is del z, this is del s, and this is del y. So sine theta is equals to perpendicular over hypotenuse. So this is sine theta, this is our perpendicular, and this is our hypotenuse. So sine theta is equals to del z over del s. So we are replacing sine theta with del z over del s. So we replaced it with del z over del s equals to 0, and finally del x and del z cancelling each other, and del s and del s are cancelling each other. So py minus ps is equals to 0 and py is equals to ps. Now the net force acting in the z direction is pz is equals to del x del y minus ps. So this we have calculated before. So here we are replacing cos theta. So cos theta is definitely, if you go to the previous picture, what is the cos theta? Cos theta is equals to base into hypotenuse. So that is del y over del s. So del y over del s is equals to replacing the cos theta. So del x cancel, del y cancel. The final remaining factors are pz from here, ps from here, and minus rho g del z by 2 from here. Since we are really interested in what is happening at a point, okay, as I said in the earlier, we are discussing the pressure at a point, okay, or we are considering a fluid element which is very small, approaching to 0. So we take the limit as del x, del y, and del z approaches 0 we get. So we can say that pz is equals to ps, because this z is very small. If we apply the limiting condition, so this factor will be approaching to 0. So here we can say that py, pz, that we have proved in the earlier case, py is equals to ps, and at the same time we can say that pz over ps. And finally we can state that the above expression shows that for every inclination, the fluid pressure is transmitted equally in all directions throughout the fluid. So based on that, we can say that the pressure is the compressive force per unit area, but it is not a vector. It is compressive because it is towards the fluid element. It is always acting perpendicular to the fluid element. So that's why it is a compressive force. The pressure at any point in a fluid is the same in all directions. We prove that the pressure has magnitude but no specific direction, and thus it is a scalar quantity. So pressure is a scalar quantity. This is finally we state that, not a vector. The pressure at a point in all fluid is the same in all direction. So now let's move on to the other topic, that is basic equation for pressure field. So here we are going to prove that how does the pressure in a fluid in which there are no shearing stresses vary from point to point. So based on this heading, or under this heading, we are going to prove that what is the magnitude of the pressure force which is acting on the surface or the object which is within the fluid. So this we are going to prove that. So to prove this, we are going to consider a small rectangular element. So this is a small rectangular element of fluid removed from some arbitrary position within the mass of the fluid. So this is a fluid system and we have taken a small fluid element, and here is the free body diagram. The pressure acting on the fluid element in all different directions is mentioned. So using the Taylor expression, the average pressure on various faces will be as shown in the figure. So here is basically by using the Taylor equation, this is the pressure force equation we are shown here. So how we did that we will discuss later on, but to prove this equation or to calculate the magnitude of this pressure, we are going to consider a dimension of a fluid element in x, y and z direction, which is del x in the x direction, del y in the y direction and del z in the z direction, and the unit vector in x direction is I and y direction is j and z direction is k. So suppose the dimension of the fluid element that we have already explained, let pressure at the center of the fluid element be designated as P. So consider the pressure acting at this point is P. Okay, the pressure at this point is P. So assume that the density of the fluid element is constant. Okay, incompressible fluid we are considering. The average pressure on the various faces of fluid element can be expressed in terms of P and its derivative. Because we know that the pressure acting at this point is P, but we don't know the pressure acting on this surface just little bit away from this point, little bit before this point and little bit away from this point, because this point is del by 2 away from this surface. This surface is del by 2 because this point is at the center. So from center the distance is del by 2, and from the center the distance of this surface is del by 2, del y by 2. So if the pressure acting at this point is P, so what is the pressure acting on this surface just after the distance of del by 2? So let's see, this we can calculate by using the expression. And what is the expression name? That is Taylor series. So we are actually using a Taylor series of the pressure at the element center to approximate the pressure a short distance away and neglecting the higher order terms that vanish as dx, dy and dz approaches to 0. So we can calculate the value of pressure on different faces by using this expression. So this is basically the pressure acting at a point, that is basically P. Okay, so if the point or face is away h distance before, if it is before, so this plus will be minus, and if it is h distance away from this point, so it will be plus. So this we can expand in this way. So here for a small value of h, because if the fluid element is approaching to 0, so that means the h is very very small, so the higher order terms may be neglected, because the first derivative is going to be small, the second derivative going to be small, since the fluid fluid element is already very small. So if you take a first derivative, so we consider it has some value, but if you take again second derivative, it will be very very small, and third derivative is going to be more small. So we are neglecting the higher order terms, so we are considering the up to first derivative. So now for simplicity, the surface force in x direction are not shown in the figure, because if I show the forces acting in x direction, this side and this side is going to be more congested and complicated and is difficult to explain. So we are considering only the forces which are acting in the y direction and z direction. So here in this diagram all the body forces acting on the fluid element is mentioned, and here you are seeing that this is the side, and at this side, and this is the point P which is acting at the center, and the pressure at this point is P. at this point. So what is the pressure at this point and what is the pressure at this point? So at this point is y. So distance from here to here is del by 2 before the point P, and this is the distance del by 2 away from the point P. So what is the change in pressure if you move del by 2 away from the point P? The change in pressure going to be del P by del Y and del Y by 2. So this pressure is going to be deducted because from here to here is P. So the pressure at this point is going to be P minus del P del Y del by 2. What is the pressure at this point? So this point is del by 2 del Y by 2 away from this point. So the pressure is going to be added. So from here to here the pressure is going to be P plus del P del Y by 2. So the resultant surface force in y direction can be written as, so the surface force, the pressure force acting on the y surface, which is equal to pressure into area. So what is the pressure at this surface which is before the point P? This is the point. So here P minus this is the change in pressure. So this is reduced. This is P, so this pressure is less. From here to here if P, so this pressure is going to be P minus del P del Y by 2 into area. So what is the area at which this pressure is acting? That is del Y and del Z. Sorry. So this is del X, this is del X, and this is del Z. Okay. So now the pressure which is balanced by the force, this is the negative direction, this is positive direction which is mentioned, minus this is minus due to the negative direction. So what is the force acting here? So this is the point we are talking about. This is the point. Okay, this is the pressure which is acting at this point. So this is P plus, so P plus del P del Y into del Y by 2 into del X del Z, the phase at which this pressure is acting, del X del Z. So this is the net resultant force acting in the y direction. Let's see if you simplify this. So we end up with the force acting on this small fluid element in y direction is going to be equal to minus del P del Y del X del Y and del Z. Let's see the force acting in X and Z direction. So in the X direction this is going to be equal to same, so here and here there is no other force than this, and in the Z direction we have this force and this force. So we can write down the net resultant force in the vector form will be, the force is a vector, so we can write down a force in this form. So the force acting on the fluid element is del Fx, and I is the direction of x axis, z is the direction of y axis, and k is the direction of z axis. Now put the value of del Fx, del y and del z here that we have calculated before. So minus del P over del X minus del P over del Y and minus del P over del Z. Del X, del Y, del Z are common. So we can write down in this form. So here we introduce another term which is called a del operator. Okay. So what is a del operator? Del operator is equal to del over del X into I plus del over del Y into J and del over del Z into K. Take the P common. Okay. So the del operator is also called the gradient of a scalar function. So what is the gradient? Gradient is equal to partial derivative in x direction into I the partial derivative of a scalar function in y direction into j, the partial derivative in z direction into k is called a gradient or the del operator. So the gradient of a scalar function that is itself a function of x, y, z is equal to del p over del x into y, del p and del y into j, del p over del z into k. So p is a scalar function which has its component in x, y and z direction. So we can write down the gradient of a scalar function in the form of del operator multiplied by del x, del y and del z. So the weight of the fluid element is another force which is acting vertically downward in z direction. That is, the weight component in the z direction, that is weight component in z direction k, minus, since it is vertically, we have considered the upward direction positive and the downward direction negative. Since the weight is acting downward, so negative sign is considered here. So minus gamma, the weight density, into volume, okay, volume of the fluid element. So the forces on the surface of the fluid element due to the pressure is equal to this, and the forces acting due to the body force, that is equal to this. So the net force acting on the fluid element is going to be equal to sigma F is equals to ma. At the moment we are considering the fluid can be in motion or in static. So according to the second law of Newton, the force is equals to ma, and the net force acting on the fluid element equal to the mass into acceleration. So what are the net forces acting on the fluid element? The surface force and the body force. So what is the surface force? Is equal to sigma Fs minus del Wk is equals to ma. So put the value of net surface force acting on the fluid element, that is equal to del p that we have calculated before, del p into del x, del y into del z, and the body force which is acting downward, gamma, the weight density multiplied by the volume, this is acting in the z direction, and mass is equals to the weight density, mass is equals to rho into v. So the density of the fluid which we considered incompressible sigma, this is constant, and the volume of the fluid element del x, del y, del z, and the acceleration. Okay. So if we simplify this, so this equation is going to be equal to, because this all factor is going to be cancelled, so it will end up with minus del operator into p, or the pressure gradient, minus gamma into k is equals to p into k. So this equation of motion can be, so here we write the equation of motion in vector form, and this equation is valid for any equation where shear stress is 0, regardless the fluid is at rest or in motion. That means this equation is valid for both when the fluid is at rest or in motion. So now we are going to study the case number 1. So what is the case number 1? So the pressure in a stationary fluid under the action of gravity. So we are considering the fluid is at rest, okay, and the fluid is under the action of gravity. So the equation we have derived in the previous slide, that is gradient, pressure gradient, minus the weight which is acting vertically downward, into density times acceleration. Since there is no motion, there is no rigid body motion, okay, so that means the acceleration is 0. So this equation will be equal to del p plus gamma k. Since the fluid is at rest, A is equals to 0, Therefore, equation 1 is reduced to equal to this, or in component form we can write down. How we can write down? So just open up this del operator. This del is equal to a partial derivative of del x into y, partial in x direction, that is del p over del x, the partial derivative in y direction plus j, the partial derivative of p in z direction into k, plus gamma k equals to 0. So, and this is a 0 vector, 0I plus 0j plus 0k. So compare the force acting in I direction, z direction and k direction. So in I direction, del p over del x is going to be equal to 0. In y direction, del p over del y is equals to 0. But in k direction, del p over del z plus, this is a k direction, gamma equal to 0. Yani del p over del z minus, sorry, del p over del z plus gamma equal to 0. So when it will come to other side, so dp over dz will be equal to minus gamma. So the above equation shows that for the fluid at rest, the pressure is only dependent on z height. Therefore, we can say that dp over dz is equals to gamma. So this equation indicates that the change in pressure is directly proportional to the height, that is dz. So we can say that the above equation is also show that the pressure decreases as we move upward in the fluid at rest. So dp is equals to minus dz, because if we are going up, if we are going in the positive direction, the pressure is going to be decreased. If we are going into the downward direction, okay, the pressure is going to be increased. So finally we can say that P is equals to gamma into H. So now move on to the case number 2, the homogeneous incompressible fluid. So homogeneous incompressible fluid means the fluid throughout this fluid system has the same density and also it is incompressible. That means it has a single row, the density is the same, and also the density is constant. So we can write down when if the fluid is at rest and also it is incompressible and homogeneous. So a fluid with uniform properties throughout is termed as homogeneous fluid, since dp over dz is equals to 0 when the fluid is at rest. So for a homogeneous incompressible fluid, the fluid density, the weight density of the fluid is constant. The above equation can be integrated as, okay. So if this is constant, this will come out from the integration sign, and we are going to integrate from the point 1 to point 2. So if you want to calculate the pressure at this point, okay, from this point, so we can calculate the pressure at this point we are considering is, at this point is considering is P2, and we are considering the pressure at point is P1. So what is the difference of pressure, or we can calculate what is the pressure at this point at P1. Okay, so just integrate, and the height from the, this is the vertical height, the reference from here is Z1 and from here is Z2. So the at point Z2 the pressure is P2, at point Z1 the pressure is P1. So integrate it. So after the integration, P2 minus P1 minus gamma Z2 minus Z1. So P1 minus P2 is equals to gamma Z2 minus Z1, where P1 and P2 are the pressure at the vertical elevation of Z1 and Z2 respectively. And the force and the pressure which is acting on the surface, it is called the atmospheric pressure. The pressure acting on the free surface is called atmospheric pressure. So as shown in the figure, Z2 minus Z1 is equals to H. So we are saying the difference between the two elevation is equal to H. So we can replace this equation Z2 minus Z1 with H. So therefore the equation 3 can be written in more compact form as P1 minus P2 is equals to gamma H. Therefore the pressure difference between the 2 points can also be expressed by the distance H as shown here. H is equals to P1 minus P2 over gamma. As we have discussed, the unit of pressure is Newton per meter square, or it is Pascal, or we can express in SI unit as a bar, kilopascal. But here this equation shows that in this case H is called pressure head. That means we can indicate the pressure in the form of height of the column of water or any fluid. So, and in this case H is called pressure head and is interpreted as height of a column of fluid of specific weight gamma required to give pressure difference P1 minus P2. So here the unit of pressure is meter if the fluid is H2O. So we will call the meter of H2O or feet of H2O or inch of H2O are the unit of pressure head. So if somebody says calculate the pressure in the form of pressure head, so we have to use this equation, okay, to calculate the pressure in the form of height of the column of fluid. So now let's move on. So most of the time it is convenient to consider P2 on the free surface. So we know that the pressure on the free surface is always known, okay, that is the atmospheric pressure, where the pressure would be atmospheric pressure, and thus we can write P is equals to gamma H plus P2. So here we can write down the pressure at this point is going to be P and the pressure on the free surface is going to be P naught. So that is, we can write down this equation P is equals to gamma H plus P naught. So equation 4 and 5 shows that the pressure in a homogeneous, incompressible and continuous fluid at rest only depend on the depth of fluid relative to some reference plane, and it is not influenced by the size or shape of the fluid container. So here an example you can see that. So this is a reference plane, okay, which is passing through the fluid system, and we can calculate the pressure on the AB surface. So the pressure at this point, the pressure at this point, the pressure at this point, the pressure on this surface throughout this fluid is same. You can see the shape of the container is different. Here is the different, here is a smaller, here is some angular shape, here is some curved shape, here is some rectangular and bigger shape. But the pressure at every point, okay, according to the Pascal law, pressure acting on a same plane, this is the same plane, and at every point on this plane the pressure is same in all direction, in x, in y, in z direction, in x direction, in y direction, in all direction the pressures are same. Thus in the above figure the pressure is same at all point along the line AB. So now the case number 3, several fluid of different specific weight. If you want to calculate the pressure at this point or at this point, here the density is not same, the density is not homogeneous, it is different. So consider two fluid of specific gravity, gamma 1 and gamma 2. So here we have 5 fluids, gamma 1, gamma 2, gamma 3, gamma 5. So consider we have a 2 fluid, gamma 1, gamma 2 contains a vessel that is open from the top. If it is open from the top, that means there is an atmospheric pressure acting on the top. then the fluid of higher specific weight will rest at the bottom of the vessel. Definitely if the fluid is heavier, it will go down. If the fluid is lighter, it will come up. Whereas the smaller specific weight will be at the top of the vessel. So gamma 2 we are considering is greater than gamma 1, and P naught be the free surface pressure, that is the atmospheric pressure. The pressure at the interface of the two fluid will be, so this is the interface. Okay, consider we are two fluid, the fluid number 1, fluid number 2, and this is the bottom of the first fluid which is heavier, that is gamma 2, and this is gamma 1. So what is the pressure? That is going to be equal to the pressure at the interface of the two fluids. So this is the interface. At the interface we have only one fluid. So what is the pressure at the interface? Here is the pressure P naught. At the interface we are considering that is the pressure P1. Okay, so P1 is going to be equal to P naught plus gamma H1 according to the equation. And the pressure at the bottom of the second fluid, that is going to be equal to, the pressure is here, what is the pressure here? That is P1. Okay, that is P1, and the pressure we are considering here, that is P2. So P2 going to be equal to P1 plus gamma 2 into H2, the height of the fluid column. Or we can replace P1 by this value with the atmospheric pressure P naught plus gamma 1 H1 plus gamma 2 H2. So this is the way to calculate when the fluid is not homogeneous, when we have a different specific weight. So this way we can calculate the pressure acting at the bottom of the solid surface due to fluid. Now here we have case number 4 that we will discuss in the previous in the later lecture. So today I am going to end up my lecture number 3 of week number 2. Assalamu alaikum.